Hello everyone. In previous lecture, we talk about electric flux and see some of the problems based on electric flux. So in this today's lecture, we see about Gauss law and how Gauss law is used to calculate the electric field and electric flux of any symmetrical surface. So let's start with Gauss law. So Gauss law basically gives the relation between the net electric flux through a closed surface and the charge body enclosed by the surface. So basically it gives the relation between the net electric flux through a closed surface. Here we talk about closed surface, which is called Gaussian surface. Gaussian surface. And another is the charge enclosed by the closed surface. So basically we can see that if suppose we have a closed surface which consists of charge q, so the Gauss law gives the relation between the net electric field coming out from this closed surface and charge that enclosed by the closed surface. So we can write it gives relation between net flux and charge enclosed. So we can say that the total electric flux through a closed surface is equal to the net electric charge enclosed by the surface divided by the permittivity of the free space. It says that the net electric flux phi net, the net electric flux is equal to the total charge enclosed. Let's suppose q is the charge enclosed upon epsilon naught. Here q indicate charge enclosed in any closed surface. So as we know that phi is equal to E dot A, or we can write it is equal to surface integral E dot dA. So we can say that the Gauss law can be given by phi is equal to surface charge integral E dot ds is equal to q upon epsilon naught. One more thing is there, when we talk about the closed surface, this closed surface is also called Gaussian surface. Gaussian surface. So we have conclude few points from the Gaussian law. First condition is that surface must be closed. Must be closed. Second, there should a charge inside the closed surface. If two conditions fulfills, then we will apply Gauss law. So we are going to see the derivation of this formula. In order to obtain the derivation, let us consider a sphere of radius r which encloses a charge q inside the sphere. Now we need to first calculate the electric flux through a small differential area ds, and after that we will integrate over the entire sphere. Here in the given figure, q is the charge enclosed and r is the radius. So first we will took a small differential area ds here. From differential area we are going to find out its vector, as we know that for the flux calculation area should be considered as a vector quantity. So we know the direction of a vector is normal to the surface, normal to the surface. So in this the area vector is given by this direction. Now the direction of electric field is same as the direction of the area vector. So in this direction electric field will be there. So we know that electric field due to point charge at a distance r is given by is equal to k q by r square. So putting the value of k we will get 1 by 4 pi epsilon naught q by r square. So according to the Gauss law, the net flux is equal to the E dot ds. So putting the value of E from the question number 1, we obtained 1 by 4 pi epsilon naught q by r square into ds. Here one more thing is that we need to notice that the direction of electric field and direction of area vector is same. Direction of electric field and area vector is same. So here cos theta is equal to 1, so theta is equal to 0. Since E and area vector are in the same direction, so theta will be 0 degree. So by putting this value, we need to put out the common things like 1 by 4 pi epsilon naught q upon r square is the constant, and here we put the ds. As we know that the surface area of sphere is 4 pi r square. So obtaining the value of surface integral of ds, we will get 4 pi epsilon naught, 4 pi r square. So from here 4 pi cancel out, this will be cancel out. So we obtained flux is equal to q upon epsilon naught. So this is the expression for net electric flux due to a point charge placed at the center of the sphere. It also expression for net flux due to point charge at the center of the sphere. This is the desired expression. Now we have seen the closed surface of various shape surrounding a charge q. The net electric flux is same through the all the surface, which means that, let us suppose we have three surfaces are there. One is S1 is there, S2 is there, and S3 is there. As we know that S1 is a spherical and S2 and S3 is not spherical. So from this expression we say that the net electric flux is constant through the surface S1 and is also constant through S2 and S3. So we conclude that the net flux through S1 is equal to net flux to S2 is equal to net flux through S3. So it is independent of the shape. The only condition persists here is surface must be closed instead of its shape and size. Surface must be closed. Now we have another point is there. The point charge located outside the closed surface. Here the point charge is located outside the closed surface. The number of lines entering this surface is equal to the number of lines leaving the surface. So from the given figure we have seen that here we have a charge which is having magnitude q is placed outside this the closed surface. From the above figure we have seen that charge enter at this location and exit from this point. Charge enter from this location and exit at this point. Enter at this location and exit at this point. So it will not constitute any net flux. That because number of lines in is equal to number of line out. So the net flux must be 0. Here net flux must be 0. So we conclude that the net electric field flux through a closed surface is 0 if there is no charge inside. If there is no charge inside the closed surface, the net flux should be 0 because the number of lines entering in the closed surface is same equal to the number of lines exiting the closed surface. Now from the given figure we need to calculate the electric flux through surface S double dash and S single dash. So for the surface S we have charge enclosed upon epsilon naught. So here the charge enclosed is equal to q1 upon epsilon naught. For the surface S double dash since it is equal to q enclosed upon epsilon naught, since it will not have any charge inside the surface, so we say that it is equal to 0. So here the net flux is equal to 0. For the third case, it is equal to q in charge enclosed upon epsilon naught. So we can say that total charge enclosed is equal to q2 plus q3. q2 plus q3 upon epsilon naught. Now another question is there. A spherical of Gaussian surface surrounds a point charge q. Describe what happened to the total flux through the surface if charge is tripled, the radius of a sphere is doubled, the surface is changed to cube, and the charge is moved to one location inside the surface. So if we talk about the first problem, then let's suppose we have one closed surface is there, we have charge inside is there. So here the net flux is equal to q upon epsilon naught. The question says that the charge is tripled, charge is 3 times, so new net flux is equal to 3q upon epsilon naught. So we conclude that for the A class, for the problem number A, the net flux get tripled. For the problem number B, if suppose the radius of the sphere is doubled, if the radius of the sphere is doubled, then what will happen with the total flux? Since as we know that flux is independent of the shape and size of closed surface. So it will not affect the net flux. Net flux will be same as previous one. Since for the case of C, the surface is changed to a cube, since whatever the shape and size is there, it will not affect in the net flux. Net flux is independent of the shape and size. So for the C, B, we have the same answer. No change in the electric flux. For the D case, the charge is moved to another location inside the surface. If we move charge from to this point to this point, then it will not affect the net flux, because the amount of charge remain unchanged. So further we have see some of the important point related to Gauss law. First point says that Gauss law is true for any closed surface, irrespective of shape and size. The term Q on the right side of the equation is refers to the all the charge inside the closed surface. Phi is equal to Q enclosed by epsilon naught. Here Q enclosed is the all the charge inside the closed surface. All the charge inside the closed surface. The term E on the left side is due to all the charge both inside and outside the surface. For this point, here we say that E dot ds is equal to Q upon epsilon naught is equal to net flux. Says it is this electric field is due to both inside and outside charge, but overall outside charge will not affect the net electric flux. We can write that outside electric field will not contribute any flux. That because number of field that coming inside is equal to going outside. Inside electric field is equal to outside electric field. So it will not affect the net flux. Another point is there, the closed surface is called Gaussian surface and it cannot pass through a point. Charge can pass through a continuous charge. We have seen earlier discussed this topic. We have whatever the closed surface is there, we called it a Gaussian surface. Now further it is says that Gauss law is based on the inverse square dependence on the distance as seen in the Coulomb's law. Any violation of Gauss law will result in the departure from the inverse square law. Here electric field is depend upon the R square, same as Coulomb's law. So that's all in this lecture. Thank you.